Hello and welcome to this A-Level Chemistry Thermodynamics multiple choice question walkthrough. Download the 15 questions from the link in the description, have a go at them, then watch this video to see how you got on. Which equation represents the process that occurs when the standard enthalpy of atomization of iodine is measured? Well, firstly, the enthalpy change of atomization of an element is the enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state. So there's two parts to that definition that will help us pick the right answer. First of all, we're making 1 mole of gaseous atoms, and so that allows us to eliminate D and B because both of those produce 2 moles of gaseous atoms. And then to decide between A and C, there is very little difference between the two, but in A, the iodine is in a solid state, and in C, it is a gas. As we work our way down group 7, the melting point and the boiling point increases to the extent that iodine is a solid at room temperature, and so A is correct. Lattice enthalpy values can be obtained from Born-Haber cycles, so that's experimental data, and by calculations on a perfect ionic model, and so that's the theoretical value. Which compound shows the greatest percentage difference between these two values? The difference between these two values arises due to polarization of the negative ion by the positive ion. And we get larger percentage differences when the positive ion is highly polarizing, so that means it's got a high charge density, and that could come from either being doubly or triply positive or from being a very small ion with a small radius. And you also get a big difference if the negative ion is highly polarizable. So in other words, it might have a particularly large radius, for instance. And so to answer this question, we need to first look at what the differences are. So we've got cesium and lithium as our positive charges. Both of these ions are in group 1, so that means they will be both 1+, but lithium is significantly smaller, so therefore more polarizing. And so we can rule out A and B. Fluoride and iodide ions are both from group 7 elements, so that means they will both be -1, but the iodide ion has a much larger radius, so it will be more polarizable. So we will get the greatest polarization for D with lithium iodide, and that will give rise to the biggest difference between the experimental lattice enthalpy value and the perfect ionic model. And so D is correct. Which of the following statements is not correct? The first ionization energy of iron is greater than its second ionization energy. Well, actually, this is not correct, and so this is the right answer for this question. The first ionization energy for any element will always be smaller than the second ionization energy for that element. B, the magnitude of the lattice enthalpy of magnesium oxide is greater than that of barium oxide. That's true because they're both 2+ ions, but magnesium has a smaller radius and so a greater charge density, and so will attract that oxide ion more strongly. The oxidation state of iron in that complex ion will be 3+ because each of the cyanide ligands is 1-. The chloride ligands are 1-, and so the copper must be +1 overall. And lastly, the boiling point of propane is lower than the boiling point of ethanol because ethanol has hydrogen bonding between its molecules, whereas propane will only have van der Waals forces. Which one of the following has the most covalent character? Well, covalent character is caused by polarization of the negative ion by the positive ion, and you get more covalent character because you get more polarization when the positive ion is highly polarizing, which means it will have a high charge density either because it is highly charged or because it is a small radius. So if we compare magnesium and aluminium, aluminium is a 3+ ion, whereas magnesium is only a 2+ ion. They're both in the same period 3, and aluminium is further along to the right, so it will be smaller. So for both of those reasons, aluminium will have a much higher charge density and so be more polarizing. And so we can rule out A and B. And then to decide between C and D, we are comparing fluoride and bromide. Bromide is a larger ion And since they're both in group 7, they will have the same charge. And so the larger ion will be more polarizable, so you'll get more polarization in D than you will get in C. And so you will get the most polarization and the most covalent character in D. This question is all about the feasibility of reactions when you've got an exothermic reaction with a negative entropy change. The table I've drawn will be a shortcut to working out the feasibility of a reaction. When there is a positive entropy change, this will be a yes for this reaction ought to be feasible from that point of view. So we can put a tick in each of these two boxes. A negative entropy change, though, suggests the answer will be no, it will not be feasible. So we can put a cross in these other two. For an endothermic reaction, that's when the enthalpy change is a positive one and the temperature drops, that means it is less likely to be feasible, so we can put a cross into each of those boxes. And for the opposite reasons, exothermic reactions with a negative enthalpy change, that will involve a temperature increase, so that will be a yes and a yes in these boxes here. So you can see now that this box has got the answers where it will always be feasible, and this one has the situation where it will never be feasible, and these two, it will depend. And this question tells us that we've got an exothermic reaction and a negative entropy change. So we're dealing with this bottom box, so it's a complicated situation, but we can at least rule out A and D because they declare that it will always or never be feasible, and that's these two boxes, which is not the situation we are in. Then we have to use the equation delta G equals delta H minus T delta S, but we're only using it qualitatively. And so if we look at this, and if delta H is negative, which it is for an exothermic situation, and delta S is negative, which we've been told it is, you can see that delta G will be 0 or less if the magnitude of T delta S is smaller than the magnitude of delta H, because that's when a reaction is feasible, when delta G is less than or equal to 0. And so for that to be the case, we want T to be as small as possible, because that will make the term T delta S as small as possible. And so that means that the correct answer is going to be C. This reaction will be feasible below a certain temperature. And that's because T delta S will get smaller as the temperature drops, and that means the magnitude of this negative quantity will get smaller, and so therefore delta G is likely to become more positive as this temperature gets smaller. Which one of the equations below represents a reaction that is feasible at all temperatures? Well, I've drawn a grid here that will help us to work this out. So if we consider entropy changes and enthalpy changes separately at first, the reaction is more likely to be feasible if the entropy change is a positive one, and so we can put a tick into each of these two boxes. And then a reaction is less likely to be feasible if the entropy change is negative, so we can put a cross into each of these two boxes. And then for the enthalpy change, when a reaction is endothermic, that means it's a positive enthalpy change and the temperature will drop, and the exothermic is going to be a negative enthalpy change and the temperature will increase. Well, it's exothermic reactions that are more likely to be feasible, so we can put a tick into each of those two boxes, and we can put a cross into the two endothermic boxes. So you can see now that this will never be feasible. These two will be feasible in a certain set of situations, and this is the box where the situation tells us it will always be feasible. So we want it to be exothermic, so that means we can rule out A and D, which are endothermic, and we want a positive entropy change. Now, when we're just simply inspecting the equations here, they're likely to be getting us to look at the number of molecules on each side of the equation. So in B, we have 3 molecules on the left and 2 on the right, which means that the amount of disorder is going to be decreasing, so that means the entropy change will be negative, so that means we can rule out B. C should therefore be correct, and it is because we've got 1 molecule on the left turning into 2 molecules on the right. This will therefore mean it is more disordered, the entropy change will be a positive one, and we are indeed in this box where the situation tells us it will always be feasible. So C is correct. Which one of the following reactions in aqueous solution has the most positive change in entropy? Well, these are complicated looking equations for ligand substitution reactions, and even if you've not studied ligand substitutions yet, you can still work this out, because all that we're in fact doing is counting the number of molecules on each side of the equation. And when that number of molecules increases, we get an increase in entropy. We get a positive entropy change. And so in A, we've got 5 molecules on the left, and we've got 5 molecules on the right. So the entropy change is likely to be really small. In B, we have 5 molecules on the left, but we have 7 molecules on the right, so this will be a positive entropy change. In C, we've only got 2 molecules on the left, but we've got 7 on the right. So this seems like a huge increase in number and a huge increase in entropy. In D, we've got 3 on the left and we've got 5 on the right. So this will again be an increase in entropy, but not as big as in C. We've got the biggest difference in number of molecules on the left compared to the right in C, and so C will have the most positive entropy change. Here we're being shown an equation for the reaction between the elements hydrogen and iodine to produce hydrogen iodide gas. We've been shown the enthalpy change is negative, so it's exothermic, and the entropy change is positive. Which one of the following statements is correct? This is a redox reaction. Well, if we inspect for oxidation states, the hydrogen has an oxidation state of 0 on the left, and so does the iodine, because they're both elements, whereas on the right-hand side, the hydrogen's oxidation state will be +1, and the iodide's will be -1. So the hydrogen has been oxidized, and the iodine has been reduced. So this is indeed a redox reaction, and so A is correct. The reason that B is not correct is it's saying that this reaction is not feasible below 298 Kelvin. Well, when you've got an exothermic reaction and a positive entropy change, this reaction will be feasible at all temperatures. C says that the yield will change when you increase the pressure. Well, that's not true, because you've got 2 moles of reactant and you've got 2 moles of product, so pressure will not affect the position of equilibrium for this reaction. And lastly, the question says that the yield of hydrogen iodide will increase if the temperature is increased. Well, since the forward reaction is exothermic, and that means if you increase the temperature, the equilibrium shifts in the endothermic direction, which is left. So that means that the yield would in fact decrease. So this confirms that A is the correct answer. This question is asking us about the equilibrium that is being shown here, and we've been presented with some enthalpy change of formation data for all of the reactants and products. And we're being asked which of these statements is not correct. In A, they are saying that the value for Kp changes when the temperature changes. Well, in fact, temperature is in fact the only thing that will affect the value of any equilibrium constant, Kp or Kc, and so this is a true statement. We could actually calculate the value for the enthalpy change by using the enthalpy change of formation of the products, take away the enthalpy change of formation of the reactants. So that gives us -394 minus -342 when we add those two numbers together, and that gives us -52 kilojoules per mole. So this is an exothermic change in the forward direction. So for instance, if we increase the temperature, the equilibrium will shift left. So this is true, so therefore not the right answer that we're looking for here. In B, they are saying that the activation energy decreases when the temperature is increased. This is a false statement, and so the answer that they're looking for in this question. The only thing you need to know about that affects the activation energy is the presence of a catalyst, or the absence of a catalyst. So changing the temperature increases the energy of the molecules, but not the actual activation energy, that minimum energy needed to start the reaction. In C, this is a true statement, because if you change the water into a liquid rather than a gas, it will have less entropy. And so since the entropy change is the entropy of the products minus the entropy of the reactants, the entropy of the reactants are going down, so that means that the entropy change calculation will end up being more positive. And similarly, D is also a true statement for similar reasons, because if water is a liquid, it takes less enthalpy to form it. So that means that the enthalpy change of formation of water will be less exothermic, in other words, less negative and more positive. So when we do products minus reactants, we will get a bigger number. And so D is a true statement, so not the answer we're looking for. So B is correct. In this question, we are shown a chemical equation for the reaction of iron oxide with hydrogen. We're shown the enthalpy change and told it's positive, so endothermic, and we've been shown the entropy change for this reaction as plus 138. And we've been given some thermodynamic data in the table, we've been given enthalpy of formation and some entropy data. We're being asked to calculate the standard entropy value for steam, and we've been given 4 options. So the entropy change can be calculated by taking the entropy of the products and adding all those together, and then subtracting the sum of the entropies of the reactants. And so our product, we've got 2 lots of iron, which is 27, and we've got 3 lots of water, which is our unknown. So I'm just going to call that W for water. And then the reactants, we've got 1 lot of iron oxide, which is 90, and we've got 3 lots of hydrogen, so 3 lots of 131. So that is our sort of calculation based on the equation. And typically we might be expected to add all these together and then subtract them and work out the entropy change for this reaction. But we've been actually told what the entropy change value is, 138. So that means that 138 is going to be equal to all of this worked out. And so that means we've got 54 plus 3W inside the first bracket, and that second bracket resolves down to 483. So 54 plus 3W minus 483 is equal to 138. So that means that 138 is equal to minus 429 plus 3W. And so therefore 567 is equal to 3W. And so that means that 1W is equal to 189. And so that means that B is the correct answer. The entropy value for steam is plus 189 joules per Kelvin per mole. In which of the following reactions is there a decrease in entropy? And we've been presented with 4 different chemical reactions and their equations. When you're faced with a question like this, they don't want you to do any kind of calculation. They just simply want you to inspect the equation and look at how many moles there are on each side of the equation. Because if there are more moles of reactant or more moles of product, they will have different entropies. And the rule is the greater the number of moles, the more entropy there is. And so in the first equation, you can see that there is 1 mole of this and 3 moles, so that is a total of 4, and it is turning into 1 mole and 6, so that makes 7. So the entropy change is 4 moles of reactant turning into 7 moles of product, so this will be an increase in entropy, and so not the right answer. And in the second example, there are 2 moles of reactant and 7 moles of product. And so this will be an increase in entropy as well. It will be a bigger increase in entropy compared to A. In part C, there are 7 moles of reactant and there are only 5 moles of product. And so that means that there will be less entropy in those 5 moles than there were in the 7. And so this will involve a decrease in entropy. So the entropy change will be negative. And so C is the correct answer. D should also be a positive increase in entropy. Let's just check that. We've got 3 moles of reactant and we've got 4 moles of product. So that will be an increase in entropy for sure based on those numbers. And we can also see that one of the products is a gas. So this will be a significant increase in entropy because one of the products is a gas and one of the reactants was a solid. And solids have very little entropy indeed. And so C is correct. This question relates to the equilibrium gas phase synthesis of sulfur trioxide. And so here is sulfur trioxide in the product, and we can see that it is an equilibrium. Thermodynamic data for the components in the equilibrium are shown in a table underneath. And so we've got enthalpy of formation data and we've got entropy data for all of the reactants and products. We've been told that the temperature is 585 Kelvin, a pressure is 540 kilopascals, and the volume of the vessel is 1.8 dm cubed. And we've been given some equilibrium moles of the reactants and the products. This question, though, is asking us to calculate the standard enthalpy change for this reaction. And so that means that there is a lot of decoy information in this question. We don't need the enthalpy of formation on this occasion. That's presumably because they might ask us more than one question about all of this collection of data, or it's simply a mean distraction. You can imagine an ideal gas equation question being asked about these data in this paragraph, and maybe a different equilibrium question being asked about the data here. But we just need this column of entropy data because we're working out the entropy change. And so the entropy change is the sum of all the entropies of the products, take away the sum of all the entropies of the reactants. And we've only got the one product, SO3. We've got two of them, so we need to include that coefficient. So 2 multiplied by 257. Then we're going to subtract the sum of 248 multiplied by 2, and then 204. And so what we're going to get then is 514 for the total entropy of the product, and then we are subtracting 700 as the total entropy of the reactants, and then this is going to give us an entropy change of minus 186 joules per Kelvin per mole. And so that means that C is the correct answer. Which one of the following best explains, so not just is just simply true, it's the best explanation for why the lattice enthalpy of magnesium chloride is much larger than that of lithium chloride? Now they've said much larger, so we're going to assume that they're talking about lattice dissociation enthalpies because those are all positive values, and language like smaller and larger is most easily applied in this case. And so if we're thinking about what makes something's lattice dissociation enthalpy large, it's to do with the attractions between ions. If we're comparing two lattices, the one that has a larger lattice enthalpy of dissociation than the other is the one where the forces inside that lattice are stronger and so require a greater amount of energy to overcome. And so this question is basically saying, why are the forces inside one lattice stronger than the forces inside another? And so A, magnesium has a greater electronegativity than lithium. Now we can't totally say one way or another which one is true there without actually having the data itself. Lithium is higher up in the periodic table, magnesium is further to the right. That's unclear. And really that's not going to be the correct answer anyway, because electronegativity is sort of an effect of other features that ions can have. In B, we're told that magnesium ions have a greater polarizing power than lithium ions. Now, this statement is true, but it isn't the reason why the lattice enthalpy is bigger for magnesium chloride than lithium chloride. It is the reason why it has got more additional covalent character in magnesium chloride than lithium chloride, but that's not what this question is asking about. It's not asking about the difference between theoretical and experimental lattice enthalpy, so it's not B either. C, magnesium ions have a greater ionic radius than lithium ions. Well, that is true, but that isn't going to make the lattice stronger. That's actually, in theory, going to make the forces within the lattice weaker, because as a result of just that one aspect, magnesium ions, you would think, should have a lower charge density overall and therefore weaker attractions in that lattice. And so that's not going to be a true statement either, or it's not going to be the correct answer, even though it is true. And so that means that the correct answer has to be D. Magnesium ions have a greater charge than lithium ions. Definitely a true statement, and as a consequence of that fact, the charge density of magnesium will be significantly greater than the charge density of lithium, so the forces inside the lattice of magnesium chloride will be stronger, and so the lattice dissociation enthalpy will be much higher. The following information concerns the equilibrium gas phase synthesis of methanol, and here is methanol on the product side of this reversible reaction, this equilibrium. We've been told that the equilibrium temperature is 68 degrees C, the pressure is 1.7 megapascals, and we've been given some moles of the reactants and product. And then we've got some thermodynamic data in the table underneath. We've got all of the reactants and products, their enthalpy change of formation, and their entropy values. This question is asking us to calculate the standard entropy change for this reaction. And so the entropy change is calculated by taking the sum of the entropies of the product and then subtracting the sum of the entropies of all of the reactants. And so that means they've given us a lot of excess information for one of two possible reasons. First of all, it's a distraction, and they want you to zoom in on the bit that they care about, and that's this column here. Or the other reason might be that this is part of a series of multiple choice questions that all use the same data set, and maybe the enthalpy of formation and this ideal gas looking information might have been used in a different multiple choice question. But this one itself is reasonably straightforward because the product is methanol and the entropy of methanol is 240, and we're subtracting from that carbon monoxide, which is 198 for its entropy, and hydrogen, which is 131, but there are two of them, so we need to multiply that 131 by 2. And so we've got 240 minus what ends up being 460, and so 240 minus 460 is 220 joules per Kelvin per mole. And so A is the correct answer. The compound lithium tetrahydridoaluminate 3, LiAlH4, is a useful reducing agent. It behaves in a similar fashion to NaBH4. Carbonyl compounds and carboxylic acids are reduced to alcohols. However, LiAlH4 also reduces water in a violent reaction so that it must be used in an organic solvent rather than a water solvent. Which one of the following concerning the violent reaction between LiAlH4 and water is false? A gas is produced. And so if water is being reduced, that means that something in the water has had its oxidation state made more negative. And so the hydrogen in water has an oxidation state of +1, the oxygen in water has an oxidation state of -2, so we must be talking about the hydrogen aspect having a gain of electrons, and that suggests that hydrogen gas is being produced, which is the case, and therefore A is a true statement, and we're looking for something that is false. B, the activation energy for the reaction is relatively high. Well, this is really unlikely if a violent reaction happens without us wanting it to happen, and that's why we have to use the organic solvent. And so that means that this doesn't need any really very much activation energy to happen, and so therefore the activation energy is not likely to be high, it's likely to be very low, to the point where we can't prevent this reaction from actually happening. And so B is a false statement, and so the answer that they're looking for in this question. For C, the reaction has a negative free energy change. That's likely to be true because this reaction just happens. It is feasible at room temperature. And so that's what the delta G is likely to be less than or equal to 0 as a result of that. And for D, aqueous lithium ions are formed. That's what will happen when LiAlH4 reacts anyway, but when it's in the presence of water, those lithium ions are going to be aqueous, and so that will be a true statement, and so B is the correct answer for the only false statement amongst these answers. Okay, that's the end of this question and the end of this video. I hope it was useful. I'll see you again soon.